Hello, and welcome to my video series. In this video, I'll be covering the difference between speed and velocity, and if time permits, I'll talk about acceleration. So I'm going to start on this slide right here. There we go. Oops, let me go back. Okay. And what I'm going to do is talk about speed and velocity. So basically, both of these measurements are measuring motion, how fast something is going. But there's two ways we can quantify that. One is with speed. The speed measures how fast. Velocity also measures how fast, but it also measures how fast in which direction. So let's talk about this in a little more detail. So average speed, when we calculate this, you might see this bar over the object that usually represents average. Sometimes you might see AVG for average, but either way, we can measure average speed by finding the total distance over the total time. So this is what it looks like mathematically, but we can simplify this pretty nicely actually and write S is equal to D over T. That's a shortcut of this, where this is our distance, our total distance, and this is our time below, like that. Okay, so let's go down a little bit. So here's a quick calculation of finding the average speed of a student. So in this case, we have a student that's going to walk forward like this, and they walk forward 40 meters east. And then they're going to walk 15 meters back. Just like this. So the question asks, what's the average speed? So the average speed is going to be calculated as the total distance over total time. So the total distance is going to be first the 40 meters right here plus the 15 meters here. In this case, I'm just ignoring the direction. We're just adding their value, so that's what distance represents. And it took 43 seconds to do that. So a nice thing to do if you're solving problems is underline your information and box the question. Or vice versa, you can box this and underline the question. Either method works. Just so you can pick out the numbers much easier as you solve these problems. So when you do that, you're going to get 55 meters divided by 43 seconds, like that. You get the following value. Let me just move this down so we can see. You get 1.28, and I'm going to round, and the final answer is meters per second. So that's the average speed of our person. So notice that it doesn't take into consideration direction, right? It was moving 40 east, 15 west, but it's just a value how fast that person was generally going. And this is a calculation of speed. Now our units are going to be meters per second, as you can see right there, simply because our units specify meters and seconds like that. So that's how you can use average speed. I like to use this version of it because it's just much more simple like that. Okay, let's do the next problem. So in this video, you can see that average speed is actually not too informative. So using the same method as before, if I wanted to find the average speed of this, I would calculate the total distance. So in this case, we have 5 miles. And the total time as it goes through becomes 0.2. So average speed is 5 miles divided by 0.2, which gives us 25 miles per hour. But you can see at any one instant that the average speed does not represent 25 miles per hour. You can see at the stoplight right here that it can be 0 or stop sign, and then same thing right here. So our average speed just gives you a general sense, not the actual speed at any point. Average velocity tells you how fast But we also have to emphasize our direction in this case. Because we're emphasizing our direction, we're actually taking a displacement and not a distance. So the final position, initial position, matters as we calculate this. Now the shortcut version, so just remember this is by definition a displacement. The shortcut of this would be this. If you know that you must take a change for both of these, that's the shortcut velocity equation. But watch how this changes the problem. So it's actually the same problem that we did last time. But now that we're considering direction, our answer is going to be different. So same information, 40 east, 15 west, 43 seconds. But now we're going to calculate velocity. So let's do that. I'm going to draw a picture again. So this person goes 40 east. And then they're going to go 15 west, which puts us at 25 when you do that. Meters, sorry. Okay. So when we're calculating the velocity, I need to know the final and initial position. So I'm going to write that on the side right here. Okay, I started at 0, so 0 will go here. And where did I end? I ended right here, which is, as you can see, 25. So I'm going to write that here. Okay, so let's calculate the velocity. It's going to be 25 meters minus 0 meters. That's my x final, my x initial, divided by the change in time, 43 seconds. Okay, so when I calculate this, I get 0.58 meters per second. Again, meters per second comes from the units of meters and seconds right here. And since we're dividing, that's where the division sign comes from. So, a couple things. Our answer is going to be 0.58 meters per second. Now, if your answer comes out positive, it's giving a direction. So notice that we kind of did this arbitrarily, unconsciously, but I did designate as the forward as positive and backwards as negative, like we usually do with a number line. So by this being positive in the end, this is saying that the average speed was 0.58 meters per second in the positive direction, so east. That's what this answer means. You can also write it like this. Now specify direction, but the positive sign does specifically mean forward. So that's how we get direction out of this answer as we look at the sign. Now, for whatever reason, if you don't put a sign, you can also emphasize it with a directional piece like forward, backwards, north, south, up, down, etc. So you can always add that in. It's never a bad thing. But notice that our average velocity was forward, which is interesting because we did have a point where we went backwards. So that's actually what this represents, that on average we were moving forward even though there was a time when we moved backwards. And if you remember from the other problem, it was about, actually, sorry, let me write it as speed. Notice that this is a larger value. So this is telling us how fast we were going, but not really the direction we were going. So notice the difference in these answers. Pretty interesting. So even though they're measuring motion, there are two ways we can do it. One with emphasizing the direction of the motion, and then this is just how fast the motion. So that's the major difference between speed and velocity. Now, when you're calculating velocity, sometimes we might have to take into consideration different times. So watch how velocity changes when we analyze different intervals. So notice here that it says from 1 second to 4 seconds. So let's mark that here, from 1 second to 4 seconds. So these are changes. Minus my initial. So this is the point where you want to use this definition if you have a change in time. Otherwise, you can do what we've done previously, but watch what happens here. X final is 2 meters minus, up here, 6 meters. Alright, T final, 4 seconds. T initial, 1 second. Okay, so we have negative 4 meters divided by 3 seconds. Gives us, I think, 1.5, but let's double check that. Sorry, 1.3. Negative 1.33 meters per second. So on average, we are going backwards. And I'm jumping ahead here. I can tell you that when we look at motion, a positive slope is forward, and yes, negative slope is backwards. So you could visually see that on average, we're going to be going backwards pretty fast. But watch what happens when we do the second problem. So I'm going to go ahead and I'll do it in different colors. So from 1 to 3. So final position is about, let's make it easy for us, I'll say 9. Minus, so I got 9 from here, and I'm getting 6. Sorry, it's above, but it's actually at the same spot. 6 meters. And then we're going to go 3 seconds minus 1 second. So 9 minus 6 gives us 3 meters. And then this gives us 2 seconds. Gives us positive 1.5 meters per second. So notice that just changing by 1 second drastically changes our velocity. This one says we're on average going backwards, where this one, between that time on average, is going forward. And I'm getting that from the signs. This needs negative, which is backwards, and this needs positive, which is forward. So you can see how your definition of average velocity changes depending on how much time is passing. Lastly, there is this thing called instantaneous velocity, where basically you take the derivative, or the limit as it approaches 0, at one exact moment. So, for example, if you look at your speedometer at any one point, when you look at that one instant, it tells you the instantaneous speed. So constant motion is different than average motion because it specifies that you cover the same distance over the same amount of time. That's the difference. So when you have constant speed, you maintain your average speed, basically. So for example, if a car went 10 meters in 1 second, and then 10 meters in the second, and 10 meters in the third second, you notice that every 1 second, the object goes 10 meters. Or instead of writing it like that, we can say 10 meters per second is the object's speed, just like that. So that's what constant motion is you maintain your speed each time, which is different from average, as we saw earlier, where your average speed can change. And you could see in this diagram that you have instances where your instantaneous speed is 0 and not the average speed, 25 miles per hour. So a car usually maintains speed because we usually don't look at the direction. An airplane, you must go in a certain direction. So if you want to fly into California, you have to go west, assuming from east. And then a copper usually gets your instantaneous velocity when he pulls you over. So in the next video, I'll demonstrate how to solve this problem.